I saw a video.
I'm going to use the other hat.
Who was it? He was like, was mad a video like,
I'm using the other hat.
Harrison Bank was like, Martin Van, it was like something. It was clown. There's so many. I had a lot of work to do.
Just send me that thing.
So today we are going to talk about rational functions. Yeah. So rational functions, and we're going to do a little review of asymptotes. So this is last year, all of chapter 6, I think. Yeah, no, 8. Chapter 8 was rational functions. So we are going to today just do kind of like a review of domain and range. We'll do a review of finding the asymptotes, and then we'll talk about if they have symmetry. Tomorrow we'll actually talk about graphing them. So today's no graphing. Just kind of like going through, remembering how to get intercepts from a function, how to get the domain and range, how to find the asymptotes, and why a graph may have symmetry. So we won't physically be graphing it by hand today. We'll just kind of rely on what the graph looks like in the calculator. Tomorrow and Wednesday, section 2.7 is still rational functions, but it's actually going through and graphing it. So we'll graph them, and then we'll talk about a third asymptote, the slant asymptote, which we didn't do last year because we didn't know division. So there are actually 3. So horizontal, vertical, and then there's one that goes diagonal. So Thursday of this week we'll review. We'll do a little review on Friday, and then your test for chapter 2 is on Monday. If you're working on the retest, make sure you get that to me tomorrow. And then you can just schedule a time to take the retest during school if you have study hall, or school. It doesn't really matter to me. Just make sure you schedule a time to take that. Questions? So, as a little review, polynomial functions and rational functions are kind of built off of one another. So we do polynomial functions and then follow it by rational functions, because by definition, rational functions are 2 polynomials, one on top of the other. So you're taking a polynomial divided by another polynomial. So if we know what polynomials are, we can throw them in fraction form and call it a rational function. There's 2 other conditions for a rational function. The second condition says q of x is not a 0 polynomial, because that would be in the denominator, and then my denominator would be 0, which would be undefined. So the denominator, the q of x function can't just be 0. And then the third little bullet there says p of x and q of x have no common factors. If they had common factors, they would cancel, and then again, it wouldn't be a rational function. So a rational function is something that remains in fractional form. And if they did have a common factor, I could cancel it, and then I'd get something that wasn't a fraction anymore. So as a quick review, without looking in your calculator, see if you can remember from chapter 1 how to find the domain, just the domain of these 2 functions. So think about how you get the domain. That was chapter 1. Dylan, do you remember where you get the domain from? No? Yeah, so whatever is in the denominator, it's not allowed to equal 0, because then that gives us restrictions of what x can't be. So Carrie, in this case, x cannot be less or minus 1. So then remember, the denominator is not allowed to be 0. So that means x can't be plus or minus 1, because those are numbers that would make it 0. And then, Carrie, how do you use that to get the domain?
You do negative infinity to negative 1 with the parentheses, and you mean with negative 1 to 0.
About negative 1 to
Or 1.
1, yeah. numbers, if you're thinking about a number line, here is the number -1 and +1. So my domain, or my denominator, cannot have those two values. But it's allowed to be anything else. So we write that in interval notation, 3 intervals, because there are 3 sections of the number line that are now divided with those two numbers that cannot be the positive and the -1. So what can't the denominator be? What makes it 0? Because that's how we get our domain. Letter B, it says f of x equals 4 divided by x minus 2 quantity cubed. So Brenton, what would make the denominator 0? Yeah, it can't equal 2. Does it matter that it's cubed, Brenton? No. It's just saying you have the same factor 3 times, but that doesn't change what the denominator cannot be. So Brenton, the domain would be? Right. Remember those parentheses get used because they're showing that it goes right up until that number, but it cannot be that number. If I had a bracket, then it would be that value. So we are going to look at the first little rational function. Again, it wants us this to graph, so see if you can graph this in your calculator. We will make just a little sketch here for ourselves. So the function is 1 over x. So graph it in your calculator, unless you know what this is. If you know what it is, awesome. Without graphing it in the calculator, wonderful. So it wants you to graph it, make yourself a little picture. It says, what is the domain? And then note the behavior around x equals 0. And we'll talk about what the little stuff underneath there means. Anybody know what this looks like? Dylan?
It's the one that goes like this and like that.
Yeah. So goes like this, and then like this. Anybody remember what the graph is called? It begins with an H. Yeah, you're so close. It's a hyperbola. So those little things that go like this and like this are called branches. So it's a hyperbola.
I had no idea. I was just spitting out gibberish.
Yeah, you're just giving me gibberish. Well, the gibberish was kind of close. All right, so if you look at the graph, you don't even need the graph to get the domain, because we don't need a graph to find domain. If I have 1 over x, what's the domain? Colin, what's the domain if we have 1 over x? What can't x be? It can't be 0, so the domain would be -infinity to? Right. So it says, note the behavior around x equals 0. What kind of line is x equals 0? It is an asymptote. Is it horizontal or vertical? If it's x equals, do you have a horizontal or vertical line? No! Vertical. So x equals 0, right here is where x is equal to 0. That's a vertical line. So it wants us to kind of notice what's going on around that location. And underneath, it gives you a little bit of, like, kind of something to think about. So as x approaches, that's what the little arrow means, 0, and then it has a little negative next to 0. We're going to see that notation randomly throughout the year where 0 has numbers or signs after it. That means from the left, so this notation, x approaches 0 from the left. So I'm on the left side of the graph. That's pretty much what it's saying. And you're approaching 0 from the left. So here's the left. We're getting close to 0. It says, what does f of x, or what does y do? It decreases. It goes down. It approaches -infinity. Any of those words that you want to use. But if I'm getting closer and closer and closer to 0, my y value is going down. So what does y do? We could say it goes to -infinity. So if I'm on the left and I'm getting closer to 0 from the left, the graph is going down to negative infinity around that line. So the same thing with the next question. As x, little arrow means approaches 0, and then the plus sign means we're on the right. So numbers actually have sides. I have a right side and a left side, or left side and a right side to every number. The minus is the left side, the plus is the right side. So it's kind of like the side that you're focusing on. So now if I'm on the right and I'm approaching 0 from the right side, my y goes to positive infinity. So essentially, the left side goes down, the right side goes up. Underneath this is the actual definition of a vertical asymptote. We usually use VA for vertical asymptote, and it says it is a line x equals a. X equals 0, x equals 5, x equals 10, x equals 20, whatever it happens to be. That occurs if y goes to infinity or y goes to negative infinity. That's what that means. F of x is the same thing as y. So an asymptote happens when your graph, the y value, kind of diverges. It goes opposite directions. One goes up, the other goes down. That happens at some value for x. So in our case above, as x is getting really, really close to 0, half of the graph is going up, the other half is going down. And that's the definition of an actual asymptote. So an asymptote happens when your graph follows infinity. The y of the graph goes to infinity, or the y of the graph goes to negative infinity. The way we find it is by setting the denominator equal to 0. So for the domain, we say it can't be these numbers because that's where our actual asymptote is. So we have an asymptote here at the value of x equals 0. It can't be that number because it doesn't exist, and that's what an asymptote really tells us. It's a place in the graph that does not exist. Can you ever cross over an asymptote? No, it's a wall. It doesn't exist. So your graph can't cross over it. It can't cross through it if that number can never exist. So looking at the example at the bottom of the page, find the vertical asymptote for y equals 1 over x minus 3. The vertical asymptote is always in x equals form, Dylan, and it would be x equals 3. It's found by setting the denominator equal to 0. A domain and a vertical asymptote go together. The asymptote creates the domain. So the domain is there because the number can't be this, which is where our asymptote is. Make sure it's in x equals form. It's just not a number 3. It's a vertical line. So x is equal to 3 creates our vertical line. Questions? So we have another one to talk about, and that would be the horizontal. The ha. So we've got the va and the ha. Vaha.
Aha!
So a horizontal asymptote happens for the line y equals. So x is vertical, y is horizontal. This definition is pretty much flip-flop. So this happens when x goes to infinity or x goes to negative infinity. So an asymptote is there to force the graph to kind of skim along a certain horizontal value. So if it's skimming along horizontally, the x is going to negative infinity or the x is going to positive infinity. You can cross a hop. So I'll say the graph can cross a horizontal asymptote. Because this isn't making it undefined, it's just forcing the graph to go to infinity or negative infinity. You will only have one horizontal asymptote. We could have multiple vertical asymptotes. Just depends what's in the denominator that makes it undefined. Horizontally, though, there's only one. And you can cross over it because it's not making the function undefined. It's just forcing the x's to kind of continue on horizontally. So you're asked to graph this in your calculator again, see if you can graph this. We can do the vertical asymptote pretty easily by looking at the graph or by looking at the equation. But see if you can just put this in your calculator. Parentheses around the top when you place it in the calculator, parentheses around the bottom. The calculator needs to know what piece of the graph of the function is in the numerator versus the denominator. If you don't group it together, it's not going to think that it's all attached in the numerator. So Reese, where would the bar be?
Negative.
Yeah, so x equals negative 1. Does anybody know how you draw an asymptote? Yeah, excellent. It's a dashed line. So vertically, we have a va at negative 1. So we're going to have a dashed line. It's dashed to show that, yes, it's there, but it's not truly a part of the graph. We use it, though, to help us graph. What's the ha? So if you're not sure, go to the table of values and just kind of make x bigger. So keep going down or going up as your x is getting bigger. You should see your y value is getting closer and closer and closer to a number. Remember, as x is getting bigger, what's happening with y? Anybody kind of see, Josh? A little less than 2. Oh wait, no, you're right. Sorry. 2, yeah, it is 2. So there should be a horizontal asymptoted 2. So that means up here at 2, we have another graph. And then Josh, where would the graph be? Where does it look like your graph is? Is it bottom left, top right? Or is it the other 2?
Yeah,
The other 2. So this guy here?
yeah.
Okay. And this guy. So when we actually talk about graphing, we will be drawing in those asymptotes with the dashed lines. They're barriers, they're guidelines kind of for the graph to follow. So the graph skims along those lines. Questions? So the last 3 things before we start looking at a couple of functions. There are 3 shortcuts to help us find the different horizontal asymptotes. So there's only one option, but I have 3 different reasonings why an asymptote might exist horizontally. So the first one talks about the degree of the numerator being equal to the degree of the denominator. And that's this example right here. So the power on the top is the same as the power on the bottom. Remember that degree is the power of your largest x. When that is the same, then the ha has the coefficients of the numbers in front. So just making a different equation for us to look at. If we had 3x squared minus 1, and then maybe 2x squared, we'll say minus 1 as well. So the degree of the numerator, degree of the denominator is a 2. When it's the same, my ha would be the coefficients. So in this case, it's 3 over 2. So 3 over 2, which if we look at the previous one that Josh found for us, we have 2 over 1, which is why the horizontal asymptote would be a 2. Powers are the same, the degree is the same, so we're looking at the coefficients in front. The second property, or the second rule, says if the degree of the numerator is less than the degree of the denominator, so the power on top is less than the power on the bottom, then the horizontal asymptote is at y equals 0. So I can keep my same function. I had 3x squared minus 1, but now I'm going to make it 2x cubed minus 1. So the degree on the top is a 2. The degree on the bottom is a 3. So when the power on the top is less than the power on the bottom, then my ha is always at y equals 0. That's because your power on the bottom is always making your number larger. When you cube something, it's going to be larger than when you square something. So the denominator is going to continue to get really big. And when you have a really big number on the bottom, eventually your number gets closer to 0. The last option is pretty much the flip. When the degree of the numerator is bigger than the degree of the denominator, then our horizontal asymptote does not exist. There isn't one. So I'm going to use the same numbers. We had 3x squared minus 1. But now I'll just put the 2x minus 1 on the bottom. And there would be no ha, no horizontal asymptote. And again, this time it's kind of the opposite case. My number on the top is going to get bigger, quicker than the number on the bottom. So my y value just keeps getting bigger and bigger and bigger and bigger. This is the case that we'll look at on Wednesday. So there's a special thing happening with this graph here. Questions? So horizontally, you're looking at the denominator. When is it equal to 0? That's where our asymptote happens, the vertical asymptote. The horizontal one, there are 3 different rules, and it's just one of those 3 rules. So whichever one it matches with based off of the powers. If you flip the next page, there are 4 different functions for us to look at. So 4 rational functions, and this is kind of how your homework is set up tonight. It's just not neat and organized like this because the book asks you these questions, part A, B, C, D kind of thing. So find the va, the ha, the domains, the range, the intercepts, and symmetry for the following functions. We're going to try and do as much as we can without a calculator, and then we'll have to look at the calculator for the range and for the symmetry. So you have to pretty much rely on the calculator for the range. It doesn't always correspond with the asymptotes, and then to see what kind of symmetry the graph might have. So let's talk about at least what we can find algebraically. The vertical asymptote. How do I find a vertical asymptote? Dylan. Solve the bottom. I need to see a minimal amount of work so that I know what you're thinking when you're writing down a random number. I don't actually have to see you solve that, but I need to know what you used. So Dylan, if we solve the bottom here, our vertical one would be at -1/2. So literally you're solving for x. The horizontal asymptote. There are 3 different cases. Which one does this apply to? Josh? Yeah. So the degree is the same. The power on the top is the same as the power on the bottom. So Josh, that means the ha is at -5/2. How can I find the domain? Brenton? Yeah. So the vertical asymptote creates the domain because that's the number that makes it 0. So it can't be that number. So every time you go to use your domain or find your domain, look at where your asymptote is, or if there are multiple ones. So we would have -∞ to -1/2. And -1/2 to +∞. Because that's a vertical line that the graph does not touch. So it stops at that vertical line, hops over it, and then starts again. If a graph could hop. Probably can't really hop. But my cute, adorable white bunny can hop. Anybody want a bunny? Sure. You have bunnies. We're going to skip the range. And then we're going to talk about intercepts. Because intercepts are important locations on our graph, where a graph crosses the x to the y-axis. We focused on finding x-intercepts for the whole first half of the chapter, so we can't let them be kind of forgotten about. How would you find an x-intercept? What do you usually do to find an x-intercept? So every time we factored for the first 5 sections, you make y 0. So we're going to make y 0, which means f of x becomes 0. So if this is 0, how would you solve for x, Carrie?
Multiply both sides by 1 plus 2.
Yeah, we got to get rid of that 1 plus 2x. So we got to get rid of this out of the denominator. Carrie, what happens if you take 0 times 1 plus 2x?
0.
It's 0. So the denominator cancels, and really you are left with the numerator of 1 minus 5x. And x-intercept is always using the numerator and setting it equal to 0. Because the denominator is going to cancel every time. If I multiply that denominator to the other side, it's already a 0 over there. So the denominator will cancel every single time. Carrie, what would our x-intercept be?
1/5 0.
Yeah, so the x-intercept is an ordered pair because it's where the graph crosses the x-axis when the y is 0. So your notation should look different than an asymptote. It's a line versus a point. So make sure you have the correct notation. The y-intercept. Garrett, how do we find a y-intercept?
Is it just setting x equal?
Yeah, just setting x equal to 0. So going back to that original problem, changing all of the x's to make them 0. Because we're solving for y. So Garrett, what would that make the y-intercept?
Is it just 1?
It's just 1. So x is 1, x is 0, the y is 1. So the last thing we need to do is get this in the calculator. We're going to find the range using the graph. So we've got to really look at the graph for the range. And then we're going to talk about the symmetry. There are 3 types of symmetry. 2 types. It's either y-axis symmetry, original symmetry, or there is no symmetry. So sometimes it doesn't have either of those options. It just doesn't have symmetry. So for the range, what does it look like the range is following in this problem? Thomas? Yeah, so for this problem, the horizontal asymptote and the range are pretty much identical to each other. It doesn't happen all the time, but this one, the horizontal asymptote and the range match up. So this is negative infinity to negative 5/2. Then I have this asymptote. 5/2, negative 5/2 to positive infinity. Does this graph have y-axis symmetry, meaning the y-axis cuts it in half? Original symmetry, meaning it's directly reflecting over the origin. So I have the same graph in the first or the third quadrant, I have the same graph in the second or fourth. And if you say no to both of those, then there wouldn't be any symmetry. So does this graph have symmetry? Questions? So see if you can look at B, trying to work yourself through those questions. Skip over the range and the symmetry until you get all of the pieces done. And I have just a little bit of work up here, not a lot. But I need to see just a little bit so that I know like what you're thinking when you're trying to find these pieces. So the vertical asymptote, you're supposed to set the denominator equal to 0. The horizontal one, we have those 3 options. We have to choose one of those 3. The x-intercept is the numerator equal to 0, and then the y-intercept would be 0 in for x. Any kind of notes that you need to make yourself? So denominator is 0, the numerator here is 0, and here we're like being x equals 0. Because it's the same for every function. You're looking at the same piece to get that information. Lauren, do you know what the vertical asymptote is? So she said, is it 1i, because you get plus or minus I. What does that mean about the asymptote? If it's imaginary, there isn't one. You only have real asymptotes. They're not going to be imaginary. So if I take the 1 to the other side, I get x squared equals negative 1. If I take the square root of that, I get an imaginary number. So that's kind of an indication that there is not a vertical asymptote. Lauren, how about the horizontal one?
0.
Yeah, so the power on the top is less than the power on the bottom, so it's just 0. So we have an asymptote here, horizontally it's 0. So if there's not a va, what's the domain? Dylan? Yeah, it's allowed to be anything. There is not a real number restriction. So I can use any x value because there's not a number that makes the denominator 0. And then if I solve for the x-intercept, I set my numerator equal to 0. I get a 0, 0. If I solve for the y-intercept, making my x 0, I end up with 0 divided by 1, which is also 0, 0. What does this graph look like? It's kind of hard to explain. What quadrants would it be mostly in? Yeah, like that. 1 and 3. So it goes something like this. Yeah. So take notice it crosses through the horizontal asymptote here at 0, 0. That's allowed. It doesn't make it undefined, so it's going to cross over it. How do you think you'd find the range? Hannah? Yeah, you need to get the max and the min because this has 2 little curves here. We have to get that max and min to find the range because the range is only in between these 2 values. It doesn't go any higher or lower than that max and min. Do you know what the max, does anybody know what the range is? The max and min? Gary?
Negative 1, positive 1.
What goes around those 2 numbers?
Brackets.
Why?
Because it stops right there.
Yeah, it stops there, and that's part of the graph. It's your max, it's your min. Those are locations, key points of the graph. Does this graph have symmetry? It does. This is the one that has original symmetry. So it crosses through the origin. The first and the third quadrants are reciprocals of each other, flips of each other, mirror images of each other. So I do want to go through C just so that we get another one of these so we can kind of see what a different graph would look like. Just work through this together. So the vertical asymptote, again, it's the same denominator as the one above. It's x squared plus 1. So no vertical asymptote. How about the horizontal? Hannah.
0.
Why is it 0?
Because the bottom is squared.
Yeah, the bottom is squared and the top doesn't have an x. So that means the numerator's degree is definitely smaller than the denominator. We said that the domain, if there isn't a va, the domain would be negative infinity to positive infinity. We'll have to look at the graph for the range. The x-intercept is when you set the numerator equal to 0. What does it mean if you set 0 equal to 4 for the x-intercept? Terry?
There's no x-intercept.
There is no intercept because 0 cannot equal 4. So that just means there isn't one. And then the y-intercept, you make your x 0. So my y-intercept would be 4 divided by 1, which is just 4. So the last thing here, we gotta just get a quick graph. This graph kind of has a mound shape. If you're in statistics, kind of looks like the normal distribution in a way. The range is this max here. It doesn't touch 0, but it goes up to 4. And this is symmetrical with the y-axis. This has y-axis symmetry. Question? So again, any graphing that you'll do, we'll be using the calculator. Some of it is kind of like looking at the table of values in the calculator and distinguishing what might be different from one graph to the next. I have 29 and 48 over there. Any interest in somebody doing 29? Reese and Alyssa, 48? Have a great day. Yeah.
Can I see that? She said it would be.
Yep.